Finish up the semester here. This is going to be the last lecture for the semester. Wow. So, the last thing we're talking about here is chapter 12. The main piece that I want to talk about from chapter 12 is this idea of a regression equation. So, what we're going to do is we're going to have some set of data, and we're going to take that data and use our calculator to generate what's called a regression equation, or like a mathematical model for that data. You guys are going to be responsible for like 6 different types of regression equations. So there are linear regressions, quadratic, cubic, exponential, logarithmic, notice for the logarithmic, we're always going to be using the natural log as the logarithm. Oops. Sorry here, guys. The exponential, I wrote the equation wrong. I wrote the power equation rather than the exponential equation. Whoopsie daisy. But I fixed it. Okay, so we have, I don't know, like 6 different models here that we're going to be worrying about. The natural question is, how do I pick which one to use? So one way is to use a scatter plot. When I say scatter plot, what am I talking about? I'm talking about representing your data as X and Y coordinates and then plotting that data, right? That's what a scatter plot is. Everybody's okay with that idea? So the shape of your scatter plot would give you some indication as to what's a reasonable shape, or what would be a reasonable model to use. So what would linear data look like? Like a straight line. Yeah. Something like that. What about quadratic data? Like some kind of parabola. Everybody knows that what I'm drawing here are just like examples, right? Like the line could have negative slope, the parabola could be upside down, or, you know, all that kind of stuff. What about cubic? That would have like 2 bends in the graph. So another exponential, that's going to have that like hyperbola shape. That's the shape that we give, or the name of the shape for an exponential graph. Logarithmic, kind of looks like that. And then the last one we have is the power model. And here we can't really write a picture because the shape of that power function can vary quite a bit. Why is that the case? notice that in the power function, the exponent is going to be dictated from the data. So if that exponent's 2, it might look quadratic. But if that exponent's 3, it might look cubic. Or that exponent's a half, it might look like a square root function. Or if that exponent is some other crazy decimal, it might look like something else, right? Is that okay with you guys? All right. So not really a set picture for that. So let's go and take a look at an example. So I'm going to give you guys some data here, and we'll kind of run through this process then. Sound good? So here's a set of data. So to decide what type of regression equation I'd want to use for this data, I would start by wanting to generate its scatter plot. Now, I would never ask you to do this kind of thing by hand because, you look at the decimals on those, like I'm not interested in trying to plot that thing. I'm going to use my calculator to do this. So if you have your calculator with you and you'd want to follow along, I invite you to do so. If you want to just sit and watch, that's cool too. Just make note of that you can go back and reference this video later on if you want to go back and review how to do this on your calculator. And I guess that holds even if you are following along, right? Okay. So the first thing that we need to do is we need to enter this data into our calculator. So to do that, I'm going to press the Stat button, which is right there next, kind of by the left-hand arrow. From the Edit tab, I'm going to select the Edit command. So you can see I already have some data in here. In fact, it's the data that you're looking at right now. I want to point out to you, if most of you, though, use probably, these lists are probably blank, right? What? Stat button, and then edit tab, edit command. No, just the stat button, not stat plot. It's by the left arrow. You got it? Okay. So if you already have data in here and you want to get rid of something, so if you only need to get rid of one entry, you can just go and say like, oh, that 48 shouldn't be there. And you can just hit delete and it'll delete out a single entry. More likely though, you're going to want to just clear the lists out because you want to type new data in there. To clear the entire list, the easiest way to do that is to scroll up to the title and then press the clear button, not the delete button, and then the down arrow, and it'll wipe the entire column of data. If you press the delete button, it's going to delete the entire list, including the title, and then it's kind of a little bit of a pain to kind of put that all back together again. If you do that, I can certainly help you. I said fix that, but it's easier to just not make that mistake. Anyways, I'm going to retype that data in now. I'm going to pause here for just a moment and talk a little bit more about just stuff while if the people following along are still typing their data in, which might still be the case. One other thing that I would be noting here while I'm typing in my data is I'd want to make sure I'm paying attention to the name of the lists that I'm typing my data in. I typed mine into L1 and L2. I assume most of us did the same thing. But if somebody had used your calculator before, you had used your calculator before and accidentally deleted a list or decided I'm going to put it somewhere else because I still want some other data I've already typed in there. You know, it might be an L3 or L4 or whatever, but you need to know the locations of your data later on when we do stuff with it. So you just want to make sure you remember where you put the stuff. Cool. All right, let's get a scatter plot out of this. So we're going to exit out of here. That was entering in data. Now we're going to generate a scatter plot. To generate a scatter plot, we're going to press second and y equals to open up the stat plot menu. You can graph at most 3 scatter plots at once, although we would never want to do that for this class, but you could. I'd only want 1 on at a time. So I'm going to pick plot 1. The first thing I'm going to want to do is select the on option so that make sure it displays this scatter plot. Under type, the first option that it's defaulted at already is the scatter plot option. That's the one that we'd want selected. Next thing we need to do is tell the calculator what is our X list. If I look at the title of my data table here, it's pretty obvious that the L is my independent variable and W of L is my dependent variable, just by the way the titles are formatted. So I'd want to use L as my X list and W of L as my Y list. I typed my L into L1 and my W of L into L2, so this is correct for me. If you had somehow typed yours into like L3 or your X list into L3, if you look at the numbers, keys 1, 2, 3, 4, 5, 6, above them in blue, you see L1, L2, L3, L4, L5, L6. So if I wanted L3 there instead, I can just press second and then the number 3. I don't want that because I did type my data into L1, so I'm going to just change that back. But I just wanted to make sure that I showed you where those other names are at in case you run into needing it. Okay. The final option is the mark. I like to use the squares because I think they're the easiest to see, but that's totally up to you. Pick whatever you want, whether you want the plus or if you want the dot. That's just a matter of preference. Okay. Next thing I want to do is set my viewing window so that when I graph this scatter plot, I can actually see the data points that I've just asked the calculator to display. The easiest way to do that is pressing the zoom button. Oh, I guess we'll exit out and then press the zoom button. And I'm going to scroll down until I find the zoom stat option. And I'm going to select that. I'm actually going to do something before I press that because I know that I had stuff in here from earlier. So you guys should have displayed something that looks a little bit like this or almost identical to this. Now, what do you suppose would happen if, say, like this data point was like way up here in the wrong spot? What's the problem? You typed in one of your points wrong, right? Like the data was wrong that you entered. So you just go back to your list and update whatever that point is you think is wrong. Double check your table that you entered in, right? Okay, so this is our shape. Which of the models, what model do you think would be the best fit for that shape? Anybody with a guess here? Exponential, okay. Anybody else have a different idea? What's up?
It looks like exponential, but like logistic equations we had where it had like the cap on it.
Okay, but logistic wasn't one of our options that we're going to consider here. Different than logarithmic. Yeah, Lily? Cubic maybe, sure. Anybody else with an idea? I'm gonna guess linear as a third one. Let's just do 3. Okay. So, we had 3 people between, Elvis and Lily and myself with 3 different ideas. All of them seem like they're kind of decent ideas. How do we know who's right? Well, there's another way we can tell, and it's a numeric way, which is nice. So there are two numeric measurements that kind of describe the fit. The first one that we'll talk about is called the correlation coefficient. And that's abbreviated with the letter R. And this really, what this does is it measures the linearity of the data. And this value for R, exists kind of on a continuum from -1 to +1. Where at 0, we'd say the data has no linear relationship. Now, this is kind of a theoretical value. In practice, I don't think you'd ever see a data set that has a 0 value for your correlation. 1 means that it's perfectly linear and that the slope is positive. When I say perfectly linear, what that means is there's a line that passes through every data or every point in your data set. So every point in your scatter plot, the line would pass through. And a value of -1, also perfectly linear, but this time the slope would be negative. So basically what we'd be saying here is that as the absolute value of R approaches 1, the data set becomes more linear. Now, the downside of correlation is that it really only describes a linear relationship, right? So when we talk about our other regression options like quadratic and cubic and the others, this doesn't really help us a whole lot. What we'd prefer to use is the coefficient of determination. Which basically describes the fit of the data to a given model or regression equation. Just like correlation, the coefficient of determination also exists on a continuum, although in this case, that continuum is just 0 to 1. Again, 0, kind of a theoretical value, implies that there's no fit at all between the data and your model. And a value of 1 would say there's a perfect fit between your data and your model. What that means is, what a perfect fit would mean is that the points in your data set would be points on the model. So like the graph of the model passes through all of the points in our data set. Everybody okay with that? Notice, what haven't I told you about either correlation or the coefficient of determination? How do we calculate them? Guess why I'm not going to tell you that? The calculator's going to do it for us. let's go. All right, so let's go back here. And what we're going to do is we're going to calculate the regression equation for each one of these three. And at the same time, the calculator is going to also give us the correlation and or the coefficient of determination. Okay? All right. So to generate one of these regression equations, I'm going to exit back out to the main screen. And then I'm going to press the Stat button. And this time I'm going to move over to the Calc menu. And if I look at this Calc menu, the first three options don't apply to us, but from there on, we have a linear regression, quadratic regression, cubic regression, quartic, which is like a degree 4 polynomial. We're not going to deal with that. Another linear regression, notice that there is a slight difference, although I don't know why we need an equation where the coefficient is named A and another one where the coefficient is named B. Like, whoop-de-doo-doo. This is our logarithmic regression. Remember, for the logarithmic regression, we're using the natural log always. So the ln regression is for the logarithmic. Exponential regression, power regression. Here's the logistic. Again, we talked about this a little bit, but not one that we're going to use. There's a sinusoidal regression, like if you want to try to create a sine function out of this thing. And then a manual fit. Again, we're not going to use the sine or the manual fit. So if we look at our list of possibilities, exponential was the first one in our list. So let's select that. Now the menu is going to require some inputs here. So we need to know, the calculator needs to know where the x variables are located. So that was in L1. For me, the y list was in L2. If you put them somewhere else, you would need to update those. But I think that the default is always L1 and L2. We're never going to use a frequency list for the things that we're doing in this class. So you can ignore that and leave it blank. I am going to use the store regeq option. So what this option is going to do is it's going to give me the option to have the calculator take the equation that I'm making and store it somewhere in the calculator so I could use it later. Since these are equations, the natural place to store them would be into the y equals menu. So I'm going to store this first equation into y1. So to get the y1, I press the vars button. I go over to the y-vars option. And then from the function option, I'm going to select y1. And then I'm going to hit calculate. So those of you following along, how many of you are missing the r squared and r values at the bottom? Okay, at least some of us are. Not uncommon. So let's fix that for you guys right now. To have those display, we need to tell the calculator to turn that option on. The command to do that is called diagnostic on. The easiest way to locate that command is just through the catalog. So I'm going to press second and the 0 button. That opens the catalog. The catalog is just an alphabetical list of every command on your calculator. Again, our command is called diagnostic on, so I can scroll all the way down through the A's, B's, C's to the D's, or what would be easier, notice above some of the buttons there's a little green letter, like there's an A, B, C, and then a D. So I'm just going to press the button where that has the green D above it. That'll jump me all the way to the D's, and then I can just scroll till I find diagnostic on. Once I've located that command, I'm going to press enter to select that command, and then press enter again to execute it. So once your screen says done, from here on out, if you run a regression equation, the r's and r squares will show up. So if I press second and enter twice, that recalls that last regression that we tried to run before. If you press enter again, it'll rerun it, and this time your R squares and R values should pop up for you. That work for you guys? The nice part is once we've done that diagnostic on, we don't need to do it again unless like our calculator's battery dies or like our memory gets reset or something like that. But like once you've done that, the calculator leaves that turned on. Okay? All right, so I'm going to write down that R squared value here. And then cubic we said was a good possibility. So I'm just going to go and redo the same thing. So I press stat, over to calc, pick cubic regression. This time I'm going to store this into Y2. There the R squared is 0.9905. Ooh, that's pretty good. So far, that's better than exponential. And then Mr. Kulik wanted to do linear. Nobody else thought that was a good idea, but Mr. Kulik wants to do it. So we're going to do it. Usually somebody suggests that. I'm going to store that into Y3. And what's we got there? 0.9289. And then my stylus wants to stop working. One note, I wanna fight you. Put up your digital dukes. We're gonna have some fisticuffs here. You know what I mean, guys? You guys have probably used OneNote enough in this class that you have probably wanted to fight it at one point or another. Many times. See? All right, so we have 3R squared values, right? Now, which one of these appears to be the best one? The cubic, right? That's the R squared value that's closest to 1. To kind of illustrate what's going on, let's take a look at the graphs of each one of these three in comparison to our scatter plot. So I'm going to press the Y equals button, and I'm going to turn off all but one of them. And then this one was artifact from a previous class, so I'm going to turn Y1 on only. I did that just by moving my cursor onto the equal sign and pressing enter so that there's only one of them highlighted. And I'll hit graph. So this is our exponential function that we're looking at. So the exponential function seems to get kind of bad towards the end, but in the beginning it seems pretty good. Let's turn that one off, and now we'll turn the cubic on. So let's take a look at that. Here's the cubic function. And boy, that's a pretty nice tight fit. Everybody agree with that? Okay. And then the last one we wanted to look at was my linear function. So let's look at that one. So in the beginning, the linear function is kind of a problem, but afterwards it looks pretty good. Everybody see that? So yeah, the cubic has the best R squared value and clearly most tightly fits the data. But let's go back and look at I'm going to put the cubic back on for a moment. And let's talk for a moment. So right now, if this data is just numbers and it doesn't mean anything, clearly the cubic is the best option, right? Very tightly fits the data. But what if we add some context to this data? What if L is representing the length of some organism and W of L is representing the weight of that organism? And we're going to try to use this cubic as our model. Does anybody see an issue there? Yeah, so like if we look at this little tail of the graph, that would imply something with a length shorter than 12 should be heavier than it was at 12. Doesn't seem very plausible. So that right away would tell us that maybe a cubic isn't actually a good fit for practically what the relationship would be between length and weight for an organism, right? If I just told you that we're looking at length and weight, which one of these do you think, which relationship do you think it would have been had we not done any of this coefficient of determination testing? I would have guessed linear also. If you think about a person, usually like every inch they grow, they probably put on like 10 pounds or something. And it's pretty consistent whether you grew, 1 inch or 5 inches. It's pretty linear in that the amount of weight gain is usually about the same, no matter how much you're growing. Or per inch anyways, whether it's going from 2'1" or 2 foot to 2'1" or 6 foot to 6'1", it's kind of all about the same amount of weight you gain. So that's relatively been my experience. So maybe a linear is the most realistic option, even though it doesn't fit our data the best of what we have. So I just wanted to talk about that for a minute because we're going to circle back on that in just a second. What's the point of making these models? What are we going to use these for? Why bother? So it allows us to make predictions, right? Yeah, so like I could predict the weight of some organism that I haven't actually weighed yet, right? I could just measure it and be like, oh yeah, it should be, like blah, blah, blah amount. So let's do that. So let's say we want to predict the weight of some organism that's 58 units long. And just for grins, let's do this for all three of our, with all three of our models, okay? So if I want the weight when the length is 58, all I'm really doing is going back and plugging 58 in for X into those models we just created, right? Well, the calculator can handle this for me rather than me typing all that stuff in by hand because that's a lot of numbers to push. To plug 58 into our exponential model, we stored that exponential model into Y1, right? So I can just go back and I can retrieve that Y1 and I can do Y1 of 58. So that gives me 27.7 as my weight for the exponential. And we'll do the same thing now for Y2. That's the cubic. So that's 34 even. And then we'll do the same thing for our linear. Oops. And that gives me 34.2. So amongst these three predictions, which one do you think is the most plausible or is the best prediction? Not a trick question. Well, the cubic would probably be the reasonable answer since it best fits our data set, right? because the R was closest to 1. Let's do another prediction, though. Let's do, say, R of 1,000, or let's do when the length is 1,000. Look at that weight. 3.2 times 10 to the 40th. That is one heavy organism. I think that thing might have its own gravity. That doesn't seem very plausible. All right, well, let's do the same thing with the cubic. Well, that's patently absurd there. What's the problem with that? It's negative weight. Well, is that like some kind of black hole or something? I don't know. That's weird. Oops, I forgot. I should just do this. Make my life easier. Okay. Well, that doesn't seem, of our three options, that's probably the most realistic one, right? So the takeaway here is that just because you're using the model with the best fit to our data doesn't mean it's necessarily going to give us the best prediction. What was different about when we tried to predict using 58? Or what was the difference when we predicted the weight for 58 and the weight for 1,000? Lily? Yeah, so there's actually two different kinds of prediction going on here. If my OneNote wanted to respond to my stylus. I don't know if this is a stylus issue or a OneNote issue, which is also the infuriating piece of this. Like, I'm not even sure what I should be mad at, but I'm mad at something. Yeah, so Lily, are you in the AP Stat class, or do you just remember this from last year? Last year. So, oh my God. All right, we'll just use my mouse. Notice that 58 is inside the extremes of my data set. In that type of situation, we call that type of prediction interpolation. And if you're using interpolation, fit really helps, right? Like making sure the best you can fit your data, the most accurate your prediction is going to be when you're doing an interpolation. Now notice that 1,000 is way outside of the extremes of my data set, right? When you're looking at that sort of situation, this is called extrapolation. Oops. If I can spell right. In extrapolation, if you've picked a model that is maybe not a very realistic model for the behavior, like the actual real world behavior that you're looking at, even if it really closely fits your data, you can get a whole bunch of nonsense when we start extrapolating. As we saw with the exponential and the cubic, we got bonkers kind of answers when we extrapolated. The linear, which felt like that seems like about the right relationship, still tended to be pretty good, right? That seems like a reasonable, realistic kind of number. You know, 1,000 is a little bit more than 10 times this, or like, what's that, about in between 20-ish times that, like 15 times 7 would get you about 1,000, or 15 times 70 would be about 1,000, right? Sounds about right. If I did 15 times that, it's not so far off, 750-ish. That's pretty close. You know what I'm saying, guys? So that's just kind of illustrating my point there about like the model that you're picking. If all you're doing is interpolation, yeah, all that matters is fit, right? If you're going to be trying to do some extrapolation, though, the model really needs to make sense for the actual physical things that you're measuring, or make sense in reality of the measurement you're taking. It's not just a table of numbers now. Does that make sense? Okay. The last thing we want to talk about is about when predictions go wrong. All right, so what are some reasons that our prediction could be really bad? We've just illustrated one reason would be you're doing extrapolation, right? Regardless of whether you think you've got the right relationship between the data, whether it's linear or quadratic or exponential or whatever, even if you have the right relationship, extrapolation is still kind of a dicey proposition. What are some other reasons that our prediction might be wrong, or we could get a prediction that's like, like nonsense? Okay, so I'm going to create a category called bad data. And I'm going to start listing things that could be there. So outliers could be a good reason. So just to illustrate, what do we mean by an outlier? Let's say that we're trying to create a function that's going to take the height of a human being and generate its weight, similar to the model that we just built. And we do this for 10 people. And one of the 10 people is like a sumo wrestler. So they're like 6 feet tall and 390 pounds. That's going to really kind of bend that curve in a way that's, may not really be very good at, even if we pick the right model, even if we pick like a linear model, which seems like that'd be a good one to pick, because we have one person in there that's such an extreme example, probably going to get us into a little bit of trouble there. Lily? Yeah. So too few measurements, for sure. Could be another reason. So again, let's say we're doing the same thing. We're trying to create a function measure to predict the weight of a person based on their height. And we just do this with 3 people, right? And say the 3 people are like, like Luke, John, and Sergio, that are all similarly sized. Like, is that going to do a good prediction for everybody? Probably not. I say similarly sized because you're not talking about like a 2-year-old and Shaquille O'Neal, who are vastly different sized, right? I understand that some of you are a little bit taller than others and a little bit heavier than others. I'm not saying that you guys look like 3 identical twins, but you're not extreme examples of different sized peoples. Okay. I just want to make sure that we're clear on this. I'm not saying that you guys are all the same size. You're just close enough for my example. John.
This kind of not about predictions gone wrong, but
Mm-hmm.
cubic equations like appear in nature?
Sure.
You have like varying relations.
Yeah, so let me think of an example. So if you're talking about, um, let's say you're modeling like the volume of something based on, like it's like a circumference or something around it. That would be an example where I expect a cubic relationship there, since the volume formula involves like length times width times height. Right, where I think a cubic relationship would make sense there if all the length, width, and height measurements are pretty similar or could be described in terms of each other, you'd create I'd expect a cubic relationship there. And then you could have something that's just like, like you're trying to create like a path of something, or like, describing like, like some architectural structure, and you're just picking points along it, and it's like an arced structure. Like a cubic might do a really good job of that, even if it's not, talking about like actual organisms, but it's something you've built or you're planning on building. Like, okay, I need, like the thing to follow this path, and that path might be a cubic path. Does that feel okay?
Yeah.
Okay. But yeah, they're not always obvious that would be a relationship that would come up a lot. And you're probably right that it wouldn't. I wouldn't expect it to happen very often. Other examples of why predictions might cause our prediction to fail. There's at least two more good ones that I think we would reasonably be able to come up with. Jacob? Yeah, so let's just say a bad model, i.e. that your r squared isn't close to 1. So for example, if we had done that, taken that data set, but we tried to do like a linear regression. I'm sorry, a logarithmic. See, the r squared value is 0.77. That's pretty far from 1. There, I would expect to not see great predictions all the time. As just an example. Does that feel okay? Do you guys get what I'm saying? Even if that's the best of the lot, I wouldn't expect very reliable predictions from something like that. What's another? There's one more bad data reason that I think would be reasonable to come up with. I wouldn't say human error, although that's not an unreasonable thing to say. Like you just like didn't know how to use your, like your tape measure properly, and you just measured things wrong. Lily?
Context, where it's not feasible for the situation. Like a negative number with weight.
Oh, okay. So yeah, that could be a possible outcome from a prediction that obviously makes it not valid, but I don't know that that's a reason that we got that prediction, like why we got a nonsense prediction, right? The other thing I would say here is bias in your data. So if you're looking at height and weight, again, you're taking the height of a person, trying to measure their weight or predict their weight from it. And let's say you did this only with professional football players were your entire data set. Do you think that's going to overestimate or underestimate the average person's weight? Overestimate, right? Like even relative for their given height, a professional football player is much heavier than the average person of the same height, right? Or if you had done the same thing just using only men, right? Men tend to be heavier than women even for the same heights. Like another way that could be easily gone wrong. Ideally speaking, how many measurements would you want? All of them is the answer, right? Now, is that feasible? We can't actually measure every single person on Earth to create our model. But what would we want? We'd want a lot, but even better, we'd want representative, right? We want like, somebody from like every age group. And you probably want a lot from every age group. And you'd want represented or proportional sizes, right? Like there's more people at age, 30 than there are at age 100. So you'd want more people in that age range. And then you'd probably want proportionally gendered, right? That each of these blocks of ages, you'd want a proportional number of each gender, so it's representative of the population distribution there.
It's like the average human weight to height ratio, and then you do like proportional representation of like the age groups women like overrepresent this like smaller age groups.
What I mean by proportional is like, say, 15% of the population is ages 0 to 10. Then 15% of your sample should be ages 0 to 10. So like you're going to not bend the curve anywhere too much at an outlier. That, yeah, we have the right number of little people and the right number of big people and the right number of old people and the right number of small people, of young people, so that everything is kind of like smoothed out and really representative of the whole population we're trying to make a model for. Does that make more sense, what I'm trying to get at there? So it's actually really hard to do your sampling, right? That's actually pretty difficult to figure out, okay, how many people from each of these do I want? And like, if I want to I have enough money to sample 1,000 people. Okay, how are those 1,000 people going to be divvied up? Like, what kind of people do I want? Where am I going to pull them from? How am I going to select them so that I get, like a good representative sample of my population? And then ideally inside of those little boxes that you've made, you'd want to be able to randomly select people from those. And ideally, if you're talking about the average human, you'd want to be able to select people from all across the globe, right? You wouldn't want just Americans, as we tend to be heavier on average than, a lot of other populations, than say like, a Japanese population, I think, are typically a little lighter than an American population. You guys get what I'm saying? So it's actually really hard to do this well. But that kind of wraps up this chapter 12. Notice that it's been pretty light on the math and heavy on the like understanding kind of what's going on. The calculator is doing most of the heavy lifting for us. Our job is going to be, like, okay, which model do I pick? Make a prediction with that model. Make a decision whether our prediction was good or bad, and why or why not. That's kind of what you're going to be asked to do on these kinds of, on the homework set here. It's just creating models, make a prediction, decide whether it's good or bad. Compare two models, like, okay, you have this one or this one, which one's going to be better? That kind of stuff. So it's mostly just interpreting what you're getting from the calculator. I'm not going to ask you to do any of this stuff by hand, which is nice. Back in Mr. Kulik's day, that's what we did. It was very, very tedious, as you had to make your own scatter plot, guess your own best fit line through the scatter plot. You pulled points from that best fit line, and you used those points to construct the equation for it, which was like a really colossally big hassle compared to just typing the data in your calculator and doing some buttons and done. So if I have like, yeah, so, we have some data like this and say, okay, well, this is going to be my best fit line or whatever. Yeah. So I would, if it's a quartic, I need 5 points. So I just pick 5 points on that line. And then I create a system of equations where I've plugged in the the values for x and y, and then I'm going to solve the system for a, b, c, d, and e, which for a five equation system sucks a lot unless you're using your calculator. Yeah. And again, with your calculator, that's trivial, but that's ostensibly what the calculator is doing. Now, the tricky part is like, how do you find the best fit line? And there's a way to do that also, but like that's way beyond the scope of the class. But the calculator is using, an algorithm that's going to find the best fit line. And even there, like how you're defining best, there's a couple of different ways that you can define that. One of them is like what do? You draw a square from every data point to the curve, and you want to like minimize the area in those squares. It's like a least squares line is one way to do that. I forget all the different methods now. It's been too long since I've had to do that. But that would be the idea. Now the polynomial ones are the worst because you need the most points for it. Like a power or a logarithmic or a exponential, you only need 2 points, which is, that's a much better system to solve than the other ones. But the polynomial ones can be pretty yucky pretty quick. So we're going to stop here. We're donezo.